Okay, the next chart here, the next few charts, are on the branch extender architecture. Branch extenders were invented in an ad hoc way to try to get around a customer problem that we were actually seeing in the field once the APPN product shipped. We had a very, very large banking customer who had many, many branch offices, like 1,000 of them. And they basically were attaching each branch offices up into a central data center. And everything was the same net ID. So basically, they had a network node that was down in this branch that would be the network node server for all the end nodes. And because there's a network down in that branch, they're part of the full APPN topology. It's a single APPN net ID. Right? So every time a link from one branch went down, we would have to propagate that information out to all of the other branches. And the links going out to these branches were not very stable at the time. So there were so many links going up and down. And by the way, if you've got 1,000 branches, you're looking at 1,000 network node topology database here, which is very large by any stretch of the imagination. So anyway, the bottom line is, it didn't perform very well because every time a link to a branch went down, you had to broadcast it to all the other branches, who, by the way, could usually really couldn't care less about the fact that the link to branch A went down. Okay, so the first thing that we decided to try to do to solve this problem was to force a network boundary between a VTM node up here who could act as a border node, force an artificial network boundary between him and each of these branches. By forcing a peripheral border node boundary, and then we'll talk about that a little bit, but by forcing a peripheral node boundary, we actually reduce the amount of topology updates that exchange. We don't exchange topology across a peripheral network boundary. So that eliminated the need for each of these peripheral, for an outage on one of these links to be propagated down to all of the other 999 branches. The problem, of course, with this approach is that now you've got 1,000 peripheral networks out there. And whenever you're looking for a certain resource, your question is, you know, which one of these peripheral networks should I search first? If each one of them had a different net ID, I could search based on the net ID of my target resources. Oh, it's in net Z? That's my link to net Z. But that didn't work because everybody down here was still in net A, the same as the data center. It was just an artificial boundary. So the bottom line really was that we ended up searching in the order that the CP/CP sessions came up. So if the LU that you're looking for happens to be on the last network that attached to you, you actually did a serial search of the first 999 branches before you got around to searching the last guy and finding your resource. So clearly, even a peripheral network boundary solution did not work in this case. So we had to come up with a way to solve this. We had to reduce the number of topology database updates and searches that were going on in the branches. We had to eliminate the trial and error searching for those branch resources. But we really did not intend this to interconnect enterprises. We intended this to be within a single enterprise. The way that we solved the problem was by inventing a branch extender node. The branch extender node is basically a node that presents an end node image upstream to VTM and a network node image downstream. By presenting an end node image upstream to VTM, we prevent the topology database flows from occurring, and we can also prevent extraneous searching from occurring, assuming that we register all the resources that can be found on or through us. All right? By presenting a network node image downstream, we give the end nodes inside the branch a network node server to use, a network node to use as their network node server. Now, the advantages to having a branch extender design like this is that end nodes can automatically register all of their resources to their network node servers. So they would register them to the branch extender. But the branch extender is also acting like an end node to VTM. And so he can forward those registration requests up to VTM saying, I've got the resources that are on me, and I also happen to have resources that look like they're on me, but they're really below me. And now VTM knows where every resource in the branch resides before he does any searching at all. And now when it's time for me to search, I know exactly where to go. So by creating a cascaded end node model, if you will, it basically gives us our ability to eliminate the topology database flows. It allows us to register our resources across these branch extender boundaries so that we get automatic searching. We don't have to do trial and error searching anymore. But the best part was we can actually do HPR flows to the border, to the branch extender. We can also do HPR through the branch extender down to devices on the end nodes, assuming that they're LU62 type of devices. So we get the advantages of no topology, we get the advantage of automatic registration, so no trial and error searching, and the best part is that we also get HPR all the way down to these end nodes. Now there are a few issues involved with branch extenders. One of them is, what happens if you put a branch extender below a branch extender? So in this case, I've got 3 end nodes that are using a branch extender as their network node. he's presenting an end node image up to this branch extender, who's acting like a network node to him, but he's also playing end node to somebody upstream. This has actually been used in some customer configurations where they had the primary data center, then they had regional data centers, and then they had the branches. And they would put a branch extender in the regional data centers, as well as a branch extender in each of the branches, and then they would all attach up to the primary data center. Right? Cascaded branch extenders works just fine. These end nodes can register to this one, this end node can register up to that one, and he can register up to VTM. So the registration requests still make it all the way up, everybody still knows where it goes. The only thing that you have to remember about the regional branch extender is that you cannot put DLUR, in fact I think that comes a little bit later, but I'll mention it now. You cannot have a DLUR below a branch extender. If you're going to put a DLUR has to be on the highest level branch extender before you get below one. All right? The other possible caveat that you might run into, you want to create parallel branch extenders. That's some high redundancy, some high availability. The problem with two branch extenders is that customers typically like to define a link between them in case there's independent LU traffic that has to go on between these end nodes, for example. The branch extender could be the network node for both of them. But what happens if one end node is served by one guy and the other end node is served by the other guy? Customers really want to create a link between these two branch extenders. The problem with creating that link between the two branch extenders is, remember that the branch extender needs to know whether he's presenting an end node image or a network node image to the adjacent node. The links over which he presents the end node image are called uplinks, and the links over which he presents a network node image are called downlinks. And if you configure this link between these two branch extenders, the question is do you configure it as an uplink or a downlink? From this guy's perspective or from that guy's perspective. It turns out if one guy defines it as an uplink and one guy defines it as a downlink, you really don't have them in parallel anymore, stated. So you can't really define them both as downlinks or else there's no way to be able to use a link directly between these two branch extenders is to put those two branch extenders on the same connection network and let the connection come up dynamically. In that case, we don't consider an uplink or a downlink, it's a dynamic connection. So what would happen is the search would go all the way from this branch extender up to VTM, come back down again, but when the reply came back, these two branch extenders would indicate that they're on the same connection network, and VTM would calculate the route between them, so the session would wind up going this way, and the path would not go through VTM at all. All right?